Although it might seem from your education so far that the structure of the atom has been understood forever, it actually took quite some time to be worked out. The idea that electrostatic charge was a thing is certainly old and goes back to the Greeks, but electrons themselves were figured out to be free particles sometime around the 19th century. If these negatively charged particles are in all matter and all matter in general is electrically neutral, there must be positively charged pieces of the matter out there that both hold the electrons in place and cancel out their charges to make things neutral. How this arrangement of charges was set up took a while to figure out. There was one popular model called the plum pudding model that said the atom was kind of this smeared out jello like blob with electrons throughout it, kind of like seeds. It turns out this didn't match reality very well because Rutherford used alpha particles. We'll talk about those later, but it's essentially helium atoms if you take away their two electrons. He fired alpha particles at very, very thin gold foil, and most of them went through and were barely deflected at all. Every so often, one would come bouncing back the way it came in, like it hit something huge. And Rutherford figured out from this that the positive charge, which also had almost all the mass, had to be concentrated in a very, very small region at the center. This is similar to what our solar system looks like. The sun has 99.9% of the mass of the solar system. And this new model is probably what you saw in elementary school, where you pretend like the nucleus is the sun and electrons move around in these nice, pretty much circular orbits like the planets seem to do. Uh, we'll see that model doesn't work for everything. It's okay for some purposes. That's why they still teach it. But there's a lot of things that we have to modify it to get use out of. One of the things that a theory of atoms and electrons needed to explain was spectral lines. So this is where we have some kind of low pressure gas and excite it by some means like an electric field. This is the way neon signs work. If you've ever looked at one and noticed there's actually a transformer there, like we mentioned a few chapters back, that turns the 120 volts from the wall up to more like 5,000 volts. And with that high electric field established across the neon, we see that what actually happens is free electrons slam into these atoms and they excite the the electrons that are still attached to atoms. If you were to look at the neon sign through a spectroscope, which is essentially like a prism, you wouldn't see a rainbow. You would see this selection of very, very thin lines. This picture from Wikipedia, it shows the sort of various rainbow stripes here, but on the far right, these are actually infrared lines that are in white, and we wouldn't be able to see them just with the naked eye. On the far left, those would be ultraviolet lines. We wouldn't be able to see those with the naked eye either, but what we would see through a prism would look like this, these various colored lines. We only see this if we look with our eyes instead of a special camera. Something like the sun or the old-fashioned incandescent light bulbs that you just about can't find anymore, the little round ones that got crazy hot and that was the source of their light, they would give you the full rainbow if you looked at them with a spectroscope. Here we're just seeing several sharp lines. This is known as the spectrum of the gas you're looking at, and every element, it turns out, has its own spectrum. It's kind of like a barcode, only in color. So if you see exactly these lines, you know you're looking at neon. Here's one. This is just in the visible, and this has the wavelength values marked under the lines. This is for hydrogen. You notice this is a lot simpler. We only have 4 lines. And we can see the wavelengths associated with each of these. And our idea is if the electron is orbiting the nucleus, it has negative energy. And we say this the same way we say it for planets orbiting the sun. They can't get away from the sun. If we could separate them so that they're infinitely far away from the sun, then we could say the interaction energy is 0. But it would take energy to do that. So if we have to put energy in to get to zero, they must be in a negative energy state right now. So that's what being bound means. It means a negative energy. Uh, if we wanted to take the electron infinitely far away, so its interaction energy is zero, we would have to add energy there. So the electrons that are attached to atoms have negative energies. As these electrons, if we add energy to these electrons, they orbit in larger and larger, again, we'll pretend like they're circles, the total energy gets less negative. So there's one huge difference between this planetary idea and the way electron orbits actually work, and that is quantization. There aren't any planets between Earth and Venus, but there's no physical reason for there not to be. We could easily put all the space probes we wanted into orbit between Venus and the Earth. But for electrons in an atom, this doesn't work. You have, for example, the third excited state and the fourth excited state. You can't put an electron between those. We will start referring to the orbit an electron is in by a number. For example, the ground state, that's as close as the electron can get to the nucleus, and we say that that's n equals 1. If we give it enough energy to bump it up to the next step, that's called the first excited state. That has n equals 2, and there's nothing in between those. There is no orbit that has n equals 1.5. These orbits are also different for every element. So since the energy of every electron in an n equals 2 hydrogen orbit is the same, and the energy of every electron in the n equals 1 hydrogen orbit is the same, the difference between them is the same. And that energy difference between these two states, n equals 2 and n equals 1, that corresponds to a photon of that energy, and that means it has a particular frequency. That's where we get the lines we'll see. Now, Niels Bohr said that the reason the orbits are quantized is that only certain values of orbital angular momentum are possible for the electrons. So again, we get back to this idea that we're restricted to have particular values of some physical quantity. That's the crazy thing about quantum mechanics. If we treat the electron as a point particle, we'd say its angular momentum is mvr, and that's just like what you found in Physics 1 for a baseball. Bohr's idea was this value has to be a whole number multiple of the h bar thing that we saw earlier. So Bohr would say mvr equals nh bar, where n is 1, 2, 3, whatever. Newton would not have expected there to be any restrictions on the allowable values of angular momentum. If we have a disk that's rotating at, say, 1.75 radians per second, we could change its speed by the tiniest amount imaginable, 10 to the minus 40 radians per second faster or slower. We would think in classical physics. It turns out in real life, which is governed by quantum mechanics, that's not true. So just like energy is quantized and matter is quantized, angular momentum is also quantized. Now, if we say the electrostatic force between the nucleus, and let's say it has Z protons, and one electron, and we say that's equal to the centrifugal force the electron feels, and if you don't like that, you can say it's the mass times the centripetal with a P acceleration. You get the same thing. We could simplify this. We cancel some r's, and we could write it as kze squared is mv squared r. We use our condition for angular momentum being quantized here to write v as n h over 2 pi, or h bar, mass of the electron times r. We plug that in, and we get kze squared equals m times this mass squared times r. We keep reducing things. We can find the radius of the orbit should look like this: n times Planck's constant, whole thing squared, over this, the 4 pi squared mkze squared. Now let's make this a little bit less ugly. Let's define something called the Bohr radius, which is going to be kind of like the characteristic size of the atom. And we'll say that's equal to h squared over 4 pi squared. This is the same as h bar squared, divided by mke squared. This gives us a distance, and it's 5.29 times 10 to the negative 11 meters. What this does for us is now we can write the radius in much more manageable terms. It's going to be n squared over z times the Bohr radius. We can also find the energy of the electron, which is going to be important. It's the same way we would do it for a satellite in orbit. We'd say, let's put the kinetic energy and potential energy together. Kinetic is still 1/2 mv squared because the electron is not moving at relativistic speeds for outer electron. This is the attraction between the electron and the nucleus, kZe squared over r. And we set these two equal to each other. We set it equal to the total energy equal to 0, like we were going to free the electron. As we start plugging in things from above, we see that we get just what we saw when we did gravitation. The kinetic part is half the size of the potential part, and the potential part is negative. So when we get common denominators and add these things, we can say the total energy is negative kz squared e squared over 2n squared times the Bohr radius, which we could also expand out and write in this horrible mess if we wanted. And this is telling us the energy of a single electron orbiting an atom of z protons, and we can find its whole energy level structure. We can just put in n equals 1, 2, 3, all of them.